Hello everyone. In this video I'm going to talk about exact equations, and in another video I'll do more examples. So two things are important to check here for exact equations. Number one is uh, the type, which means uh, is this an exact equation, and we need to do a test of exactness. And the second part is the method to solve. Okay, so the background I'll give you here is, let's say if we have uh, a function, a mathematical function that represents some physical idea or behavior or physical quantity, all right, and this function happens to be constant, let's say in xy plane, and there are many applications to this, then this differential, or df, and I think you've seen it before, which is called total differential. It's just going to be the partial derivative of f with respect to x dx plus the partial derivative with respect to y times dy. It's going to be 0. So I'm trying to do this in a concise way so you see the two things that are needed, and will make actually this easier than it looks. So here, what happens? This partial fraction of f with respect to x, let's call it m of xy. And this one here, this partial derivative with respect to y, we'll call it n of xy. And so we have this equal to 0, and that's a definition for exact equation. And of course, the only other thing to mention when it comes to the exact differential form, and use the differential, let's see, give you more. So this differential form, m dx plus n dy, and of course when it equals to 0, then we will say it's exact. And of course here what we did is m is this partial derivative with respect to x. I want to show this because it's important when you solve to connect back m and f, or n and f, right? So if we have these for all of x, y, or points in some rectangle region like the one I explained before, then this differential will satisfy the exactness. But of course, you want to ask the question, is there a way for me to know that some equation or differential equation is exact? Well, there is some calculus theorem, of course, concerning the quality of continuous mixed partial derivative, because we want these to be continuous. then this exact form equal to 0 means that the partial of m with respect to y, and I think if I do it in the same page will help. So this, because you see this dx, so the partial with respect to y, you switch them, and this one here, because you see here y are equal. So that's going to be the test. Okay, so the test of exactness is just going to be this. Two parts are equal. All right, if we check they're equal, what do? We go ahead and solve. So the method, I want to explain the method, not go into the details of math like integration or integration by parts and stuff, because I want you to kind of to get the idea first. Then we'll do that in examples. So the method is, once you find out that they are exact, and of course these are continuous, this m and n, of course, because we use this because of this condition here that continuous in some rectangle R for all xy, of course, or I should say maybe in R. All right, so what do? We're going to, because the connection of m and f, we're going to say this is the function that we're looking for. Let's integrate that part here, and we're going to be missing some function that is dependent on y, because I picked m. If you pick n, then you're going to have some h function here that is dependent on x. So you have two ways you can solve these, and of course when you look at the examples, whichever is easier to do, you go with that one. But let's say you pick m and you set up the formula for the function to be this way. Of course you're going to check the exactness, then you set up this, then you're going to find this formula, and once you find it, you're going to differentiate now with respect to y. So I started here m dx stuff, then I will differentiate with respect to y. That's why I give you the introduction, because now you will say, I know I've seen this here to be this, right? So the formula that you get from this derivative, you will match with n of x, and what that will do, it will give you g prime of y, and once you know g prime of y, you know gy, and once you know gy, then you have the function. Okay, so maybe I'll just do this overall in an example, then in another video we'll do more examples with more details. So let's show this example. Let's say you need to solve this here. All right, so you will do the test, which is the partial derivative to this. And you will do the partial derivative of n with respect to x. As I mentioned here, I'm not really to go in details with the math, but when you try it, you pause the video and check both of them and see if you get 2x. And once you get they're equal, then you'll say yes, and that puts you to go ahead for next step to solve. And here, let's say I pick m. So I'm going to reverse m here. So I'll integrate m, which is again this part, plus some function with respect to y. Again, you can check. I'll give you the answer, and the purpose here is just to show you the overall solution method, because it looks like it's long, has multiple parts, but really once you see this big picture, it's not that bad. You'll understand what's going on. All right, so now when you do this part, what happens is we don't know what g of y is. And since I used m, I'm just going to go to n. But how do I get n? N is this derivative with respect to all right, let's see. It's it's not picking up, but here it is now. It's picking up. Okay, so when I do with respect to y, when I do this derivative, I should get n of x, y. So now doing this here gives you, remember again, differentiate with respect to y. When you differentiate with respect to y, x squared is a constant, so that's x squared. Tangent of x doesn't have y in it, it's a constant, so derivative is 0. Then g prime of y. Then what is n of x in the given equation? All right, so I'll let you find it first. It's x squared plus 2y. It's equal now to x squared plus g prime of y. And now you'll ask, what is g prime of y? Okay, if you say 2y, then that's correct. Good job. And now, once we have this, maybe I'll do it here so we'll keep all in the same page. So if g prime of y is 2y, then g of y is y squared, right? And now that gives us this solution, and replace g of y with y squared. All right, so the solution is now x squared y minus tangent of x plus y squared equals to some constant c, and it is in implicit form. And once you have in implicit form, you can see if you can switch it to the explicit one. But here, right, it is in implicit form. And what else I need to mention here before I move on is, yeah, when I did the integration, you see that a constant is going to be generated, right? Let's say call it C1 or C2. And so what happens at the end is, if you do that, you will just combine these constants in C at the end here on the right side. So that's kind of the only other thing that needs to be mentioned. Okay, thank you.